Hi, can you all hear me? Can you hear me? Test mic, 1, 2, 3. Okay. Okay, I do not know why I cannot share my application, but if that's the case, I think I'll need to share my entire screen. So just to make sure that you guys can see, can you guys see my PowerPoint slide now? If yes, you can text, else I'll just move on. Can you guys see my Microsoft PowerPoint just now? Okay, good. Thanks. Okay, a bit of a recap. I think last week we did a bit of a study on the I/O application. We studied on the a bit on a case study how to do masking using the functions, the XOR functions, the toggle function, the AND function, and the OR function. Now that part is actually based on passive aggression. Okay, so take note of that. I think as maybe when we reach towards the final, I will give you guys some more questions. But those are the frequently questions that frequently pop up. Okay, and the I/O ports, selection of I/O ports, all those are some of the stuff that I actually grabbed from the passive questions. They might not appear because the UC have changed, but nevertheless, these are actually good application studies. Make sure in your lab, right, you actually attempt to do it. These are the lab that you'll be able to learn, especially this lecture. This week's lecture about the assembly language. These are actually very important stuff. Coding questions can actually come up from this week's lecture. It has come out, and it's good for you to familiarize yourself with assembly language. I think probably in your 4th or 5th lab, you'll be doing a lot of assembly language. Now, assembly language is actually very important. I think in the very first lecture we discussed on the instruction set and all this. These are all related stuff. All right. Assembly language is basically just one level higher, and I hope that you guys take the effort to learn the various instruction set, the assembly instruction sets. Okay. Most of you, 70–80% of you, will just skip through this lecture without actually real understanding on the assembly. We have a lab that actually is dedicated for you to understand more of the assembly, and that shows how important this assembly language is. What is assembly language? Later we'll come to it, but I appeal to you guys. This is a very important topic. Don't skip it. Some of you will have that mentality. Hey, I'm probably not going to use it because I'm an electrical engineer and stuff like that. These kind of things will be useful because you do not know what field you'll be getting yourself involved in. And assembly language is a very broad field that will enable you to go into different parts of various companies, especially electronic companies. You want to work in places like embedded system companies. Assembly language is part and parcel to optimize the programming functions. Many of you will say that, I already know all these kind of wiring language, C programming and stuff like that. Well, those are good for hobbies, but when you actually go to a higher level, you really want to optimize the program. Some of these programs, like for example, a print line or whatever, they are not optimized. So when you want to do something that's so customized and so optimized, that's where the assembly language will actually come in. That's very important, okay, when you want to write libraries and so on and so forth. That's where the knowledge of assembly language will come in. Let me check if there's any chat. Okay, no chats. All right, good. Just let me have a attempt, see whether I can share my my application. Yes, okay. So now it has appeared. Okay, so this week we're going to talk about, we have two lecture series, two lecture weeks on just on this instruction set. So you can see how important is this thing. Today we're just going to discuss the overall, and we're going to try to categorize some of the instruction sets. What are they for? How they use? Lecture. The second part of this lecture will go more in depth on how to use all these instruction sets. There are approximately 20 plus instruction sets. Different have different slightly variations of instruction set, but more or less they are the same. Okay, jump, move, all these kind of things are more or less the same. All right, but there are slight differences in instruction set. Most of the microcontroller will have approximately 30 instruction sets, so it's good that you can immerse yourself in all these instructions. Okay. In this lecture, we're going to talk about register transfer notation. So register transfer notation is basically a shorthand. Okay, it's how you take notes, how you transfer stuff in the memories, and so on and so forth. It's not a programming language itself. It's basically a way of expressing what you want to do. But when you really code it, you code it in assembly language. Okay, so transfer notation is mathematical description of what you want to do. Okay, so any physical implementation, you need a type of language to be able to express whatever that you're doing. Okay, so if you're doing let's say dynamic system, there are calculus involved to explain whatever that you try to implement in a mathematical form. Now, this register transfer notation is basically the similar type of stuff. You apply it to actually express the programs and all this kind of stuff that you want to. All right. We have the second one is machine language assembly language instruction. Now, I'm going to get this very simple. Machine language is the lowest possible language. If you can read machine language, that will be the best. Okay, you do not need any assembly instruction or C programming. So assembly language is used to compile into machine language. It is those stuff. If you played with last week, I think just going to dig out some of the stuff. If you guys have done the labs, the virtual labs, you find that when you press compile, a lot of junk code actually come out. They are actually hex values. Now, those hex values are what you did in C. You compile it into assembly assembly, then further into machine language. What you see in the memory is a machine language. Nobody can actually go to that level of understanding a machine language. Is too mathematical, and it's very difficult. There was this movie that one of my favorite movies that very long time ago, I think it was in the 90s or early 2000. The movie is called Matrix, and there was this guy that's able to read codes, machine language, without anything. So when he see a bunch of numbers appearing on the screen, he knows the character is actually running through a tunnel and whatsoever. So that guy can actually read machine language. That's the only example that I can give you. That guy reads machine language and able to find out actually what happens on the screen. Okay, so that guy is amazing. But the reason why we engineers came up with the assembly instruction is because it's very difficult to read in language. It's possible, but it's very difficult. So we don't want to make ourselves difficult. Then the third thing that we're going to learn in this lecture is that the types of instruction. What are the different type of assembly instruction? Okay. So Basically, in the instruction you have the operand, the operator, and then you have the it just goes along that format. Okay, but different operator will give you different results. Like for example, I give you just a very simple one. Okay, in mathematical operations, you have logical operations, and you also have mathematical operation. Mathematical operations are minus, plus, divide, multiply. Logical operations are XOR and OR. So those are the different type of instructions that you can use, and they are categorized as assembly language. Okay, so the architecture and operation of CPU depends on its instruction set. Okay, remember back what I taught you guys. Instruction set, architecture. Okay, so the architecture, you have reduced instruction set, you have reduced instruction set, you have complex instruction set. Okay, please, we try to relate with whatever that we are learning along the way. Okay, so over time we'll just try to relate back. I'll let you guys know. How to access operands, meaning to say, if I want to transfer one information from one register to another, there are different ways of doing it in terms of coding method. Okay, now these coding methods are what we call addressing modes. Okay, and they will affect different things. Like for example, I'll give you a very solid example: copy paste in your file. Okay, now both of the things does the same thing. You copy from C drive to D drive. All right, a file, a picture, and you cut and you paste. Now these two things actually, they do the more or less the same thing, but the result is whatever that you have initially. If you use cut, it will be gone. Okay, but if you use copy and paste, whatever that originally remains in the C drive, it doesn't. But both of these will result in the D drive having a new file, a picture. Okay, so these are just different modes. If I ask you what are the different modes of getting one file to another place, okay, you can say you can control C, you can copy and paste, or you can cut and paste. Okay, let me check if there is any chats. No chats. Okay, that's good. All right. Now, I also have checked. I think participation on the YouTube, especially on the I/O, it's quite low. Okay, so if you guys find that this lecture very difficult to understand or tutorial very difficult to understand, please let me know. I will adjust it according to your level so that everybody can benefit. Right? So if you find it very challenging, please let me know. Okay. Okay. So addressing mode is basically the different ways of how we copy and paste, and the result, the process is the same. Result will be a bit different, but they do more or less the same thing. Instructions are stored in memory like any other word and be decoded by CPU during instruction cycle. Again, something that we discussed along the way. Instruction cycle, you guys still remember? You extract one instruction, load it into the CPU. Okay, CPU will do the fetch, decode, execute, fetch, decode, execute. Now, how do I see what is the content of the memory? When you type a C programming, the interpreter in your integrated development, okay, your IAR, integrated assembly, whatever. I also forgot the name. Okay, but it's the IDE. So this IDE actually takes the instruction in your memory that you have coded, and it actually compiles it, and it extracts. It's being saved in the memory, and when you run the program, it keeps on extracting individual instruction sets from the memory itself, and it loads. Okay, so I'll give you an example that I always give. Let's say, for example, you are blinking an LED again and again and again and again. Okay, now these kind of simple things you can write it in C programming, compile it, okay, in the memory, and it will start from the boot address. You go to the memory, okay, and it will just keep on repeating and repeating and repeating. Okay, when you guys do programming engineering, very easy for you. All you need to do is while bracket 1. It will keep on repeating again and again. Okay. But in the case of assembly language, we want to know how is it done. Okay. So C programming, it's a language for the user, for the programmer. Okay. But the machine, the computer understands only numbers. All right. So C program in a way, it's a program for humans. Okay, you can speak with your friend next to you using C programming language. Is it possible? Yes, it's possible. I've done it. Okay, but the machine doesn't understand C programming, so you must have an interpreter to convert your C programming into lower level language, like machine language. Okay, so C programming is a user language. It's for humans. It's not really for computers. A lot of people misunderstand. Okay, so when your business friend asks you, C programming language, is such a high-tech language. Actually, this language is a language. It's just like mathematics. It's just like English, just like Malay, Hindi, or whatever. It's a language for the human, and this language is designed in such a way that it's easily converted into machine language. Okay, we're going to see how that works. Why do I say that it's easily converted? Because it's designed to be in a convertible to machine language, and this process is easily convertible to machine language. There's a step-by-step instruction to convert your C programming into machine language or your assembly language into a C programming language. Now that's one of the reasons why C programming is so suited to use for different embedded systems. Have they found out an easier way or a more acceptable way? Nowadays, there are some guys who are trying to port to make Python to become the #1 programming language for assembly. Okay, it's called MicroPython. You can Google it up, MicroPython. I myself was never interested in this kind of thing because my work is mainly I was born in an era where C programming is bread and butter in my life, so I'm very comfortable with C programming. For you guys that want to explore MicroPython, okay, but the process is the same. It's only the interpreter that's able to convert whatever language that you understand into machine language. It's the same process. Once in a while, the interpreter might not be so optimized or so optimized. All right. So, for example, in your C programming, you write while one and then you do a blinking LED or whatever. Okay, that's straightforward. But the interpreter interprets it and converts it into machine language. Bear in mind, it's an interpretation. So the program interpret the whatever that you write in C programming, and it convert it into is done automatically. Now, in this case, it might not be so optimal. That's the reason why you need to program a lower level called assembly language. Okay, assembly language is quite near to machine language. The variations of different ways of interpreting is very low. Okay, so machine language is another low-level language. Okay, I used to for my final year project those days. Okay, it was a very low level. We do not have so many tools at that time. So during those time when you're able to design something that's just design a very simple thing that's considered quite good. Okay, those days you do not even have Arduino Uno wasn't in the market, so we need to construct everything from scratch, from a chip, then industrial chip. We need to design using PCB, fabricate the own board, and we need to redesign everything. So my FYP project was designing a robotic controller board for competition purposes using PIC 18F877A. All right, and instead of using C, I choose to do everything in assembly language. Okay, line following program. Grabbing things, program, everything is done in a modular form in assembly language. So if you do things in assembly language, it's very optimized. Okay, if you write a program and you want it to be very fast without any access cycles, computer cycles, you really need to do it in assembly language. Okay. lecture next week, lecture will focus on software components of the CPU. Okay, so this is fair enough. We cannot compress everything into one lecture. For programmers, detailed description of hardware is not required. For some of more important concepts, what register, CPU, memory, maps, instruction set. Okay. Hardware details become important when programmer wants to fine-tune, optimize, debug. You see, this is the point. When you really want to do something that's highly optimized, you can use assembly language or you can really fine-tune. But why do we not consider all these things today? You know, why do we take for granted this three issues: fine tune, optimize, debug? The reason why debug, we still debug, okay, but fine tune and optimize, these are the two things that we always take for granted. We don't care at the moment. You know, what's the reason why we don't care? I tell you why we don't care. We don't care because we have so much computation power in the palm of our hands today. Okay, you buy an Arduino Uno or you buy an MSP, they are so powerful. Okay, in fact, if someone would have an MSP or an Arduino back in those days when they launched the Apollo program, they would have done much better. Right? They could have done everything in one CPU or whatever. Okay, but today we don't care about fine tune and optimize, but it doesn't mean that it's good practice. Now I tell you why it's not practice. Computation cycles, okay, and computation cycles. If you have more computation cycles, you tend to consume much more power. Okay, ever thought about why your phone is so stupid? Why some phones are so good and why some phones are so stupid? It's because some phones are designed, the OS is designed in such a way that is not optimal for that hardware, right? So that's why once a year, I think Android, they will have a type of a handphone that they claim will have the most optimal OS to hardware combination. Okay, so that's part of fine tune and optimization. Now, with regards to whatever that you're learning, optimize means reducing programming lines and so on and so forth. You hold on a second. I need to attend to something. Okay, so the method of fine tuning and fine tuning a program, something that people take for granted. Many people said, you know, it doesn't matter. Why do we spend so much time in fine tuning something that you know, it's we have a lot of memory space and capacity. It's very good. Okay, so nobody actually cares. Hold on, okay. Okay. Now, a register transfer notation is a type of written language that helps us to express what goes on in the MCU, operations in the MCU. This part we will study the basics because you have 14 weeks to study. There's so many things to do. Okay, you can focus on basically so many things. But I'm just going to touch on rotation transfer notation and give you some exercise that I prepared on the tutorial, and there are also some exercises on the textbook. Okay, please go and read your textbook on this. Save some time for you to explore more on assembly language rather than register transfer notation. Register transfer notation, so it's basically a language. Is just a language to express what happens in the register. All right. So the language actually looks like this. There is a source, then there is a destination. After the execution of execution, contents of a register or cell in the memory may be written upon with new data. So, for example, move information from one register to another. The source, okay, you move from the source to the destination. So just remember this flow, okay, from the source to the destination. So when you you read the template, okay, it says SRC means it's the source, DST means it's the destination. So it's more or less expressed in such a way, okay? So expressed by the value or predicted, so constant, okay, so this one, for example, 24, my constant. So this one is, you can use, okay, wait, what is this? This is a bit confusing, this part. Express, okay. For example, 24, my constant. Okay, so basically this is expressing how can constants be the source and destination, how can they be the link, the register can be linked to a constant, okay? So this is the register, and this is the value, and this is the name, okay, of the register. So this is the how you express a constant in a register. They cannot be used in destination, okay? Okay, referred to by name in the extract. Rn is used where and okay. Anyway, these are just description. I will later go through. There's one slide that makes it very obvious. Okay, now this slide make it more obvious. We just skip the previous two slides because it's very confusing. Just look at this. All right. This one is extracted from the textbook, okay? Now let's say that you want to save the content, the memory content, you want it to be this, and you want it to be, assume it's a word size data address before. Okay, so look at this. This is the source. Okay, there's always an arrow in register transfer notation, okay? Now this is just a way of expressing it, okay? So whatever the content in this memory, okay, you want to save this constant in this memory, okay? So store 028 ch at address, okay? So whatever this 28C will be stored in this address, okay? Copy a memory location, okay? A word, okay? So whatever that's in this location, okay, the content will be stored in this this memory, okay? And then you have the value, okay, stored in this. This is a word, this is a byte, okay? Add 3847 to the current address. Okay, so this is an addition, okay, and what you have is basically this, okay? So you can see that what is, just by looking at these four examples, you know that the format actually goes like this, okay? There is a source, there is a destination, and then there is an arrow. Now, why do the questions some of you might have, why do we follow this method? Well, this is a method that was been widely accepted by programmers. You go to a company and a bunch of guys start to write their instructions this way. So just bear in mind that this is what we call register transfer notation. It's normally used for embedded system design to express your idea, okay? So questions can come out in this way. What is the result of the after this? What does it mean after this register transfer notation? So this is basically the right hand side is what it means, and this is in English. All right. So you express your register transfer notation with this annotation: the source, the destination, the source, the destination. The source will always be on the right hand side, destination on your left. All right. When we started this unit, we reviewed to you that instruction sets are very important. When you write in C programming, they are actually compiled, interpreted in machine language, okay? And this machine language actually represent, it's a 16-bit or whatever, they actually represent something. If you can read this, you're basically very competent in this assembly language, you know. So they are actually separated into sections. So you have a 16-bit. Okay, what does the first byte means? 16-bit. What does the first byte, second byte? What do they mean? Okay, the first four bits second 4 bits, third 4 bit, and the most significant 4 bits. What do they mean? All right. So we're going to just roughly go through what do they mean. These are what we call instruction sets. So we're talking about machine language. Okay. So machine language, when you compile it, you press compile in your last week labs, you'll find that, hey, there's a lot of junk numbers or hexadecimals. You know, what do they mean, right? So this is actually what they mean. Okay, the 16-bit instruction, it normally comes in 16-bit, right? They have opcode. Okay, the most significant one means the most significant 4 bits. Okay, or the most significant 4 bits. They are what we call the opcode, known as operating code, which defines the operation to be performed. Okay, so whether the operation is an add, the operation is an or whatever the operation. So the first most significant 4 bits decides that. All right. Wait a minute. I think I might have missed out on. Okay, recording. So the most significant 4 bits actually determines the opcode, or for layman, it means the function that you want to consider, whether it's an add function, or function, or whatever. The operand is the data or the register used in the instruction. So let's say, for example, you want to add the value of 2 registers. What is the opcode? The opcode is an addition. Now, what is the operand? They are the values in the 2 registers. Okay. Now, what is the addressing mode? Addressing mode is a way in which the operation defines the data, for example, an RTN expression, R or Rn. Okay, so these 2 things are different. This is the memory itself. This is the location pointed by the memory. Okay, so it's a bit different. Again, the easiest example I've been thinking, I think the easiest example, almost equivalent to well, it's not good. If I give that example, it would cause confusion. But never mind, we look at some of the examples. This is pointing to the address itself. The address as pointed by the memory. The value in that memory, that is the address. Okay. You need to look into this. There's a lot of tricky questions that come out from this addressing mode. I will give you some examples. Okay. Following the opcode, they may be information of 0, 1, or 2, 3 operations depending on the MCU. There's a bit of variation, but it doesn't matter. Okay, so for this unit, we just assume that we are working with MSP 430, exactly like whatever is in the textbook. When you go for your embedded system engineering, it's the same thing. You'll be using the same platform. We do not want to change here and there, so just stick to this platform. In the future, you might explore microchip, very typical, famous Freescale or whatever in your workplace. It's transferable. The knowledge is more or less the same. All right. But for the purpose of making this unit smoother, just stick with the textbook and the unit that we want to explore, MSP. All right. Okay. Following the opcode, you may be 0, 1, or 2 operands, or you can even have 3 operands. Okay, in the opcode. So you can have an opcode, a function that involves 3 operands. Okay, now let's look at this. This is very clear extract from the textbook. Okay, so this one is from figure 3.23 from textbook. You can refer back. Okay, now the first 4 bits is 16-bit. You have your operations. So this first 4 bits will tell you, okay, what is the operation that you want to do, whether it's add or whatever. Source info, okay, where do you want to get it? Okay, addressing mode, okay, whether you do it like this or different addressing mode, that will cover, no problem. And this is the destination. Okay, so if you see this code, okay, let's check out. Translate this into hexadecimal. Can you do that? Okay, so 100, I know this is an 8. Okay, 80. Okay, what is this? This is a 4. 480. And what about this? 480. This is probably about 480C or D, I'm not sure, I think it's a C. 480, okay, 480D. 480D, the instruction is 480D. So the computer will extract 480D from your memory, and this 480D represents this thing. Okay, which opcode later you guys can explore yourself, but generally just to tell you that, you know, a question can come out, okay, it's 16-bit opcode, these are 16-bit instructions, what do they mean? Probably give you a table, okay, okay, so it means that extract this one from this one, you know, using what addressing mode, you know, what the operations, you know. So it's this is a machine language, it's an instruction, okay. Now when you compile, this is what you see. Now what you need to be able to achieve is you need to be able to relate to all these kind of things, okay. So let's say, for example, I give you an RTN, you need to you know, relate back to what does this register transfer notation means, and this transfer register notation means 480D. 480D means is a very specific instruction. It does something, transfer from one location to another. This one is another, and you can have different machine language, but they should be expressible using register transfer notation. Okay, assembly language. Now this is a different one. Don't get yourself confused. Whatever that we discuss is what we call machine language. Okay, it's a hex. So you see, you press compile, you see a bunch of junk memories. You know, a lot of characters in the memories. Those memories are whatever contains the memories are basically this. Okay, these are a machine language. But now we want to go back into a slightly higher level. Okay, now if I stretch my hand, okay, you can do so in your own place. Stretch your hand. I always do this for the past 3 years so that I can explain in a very clearer method. Stretch your hand. Okay, on your right hand side are high level language. On your left hand side are machine language, the lowest level possible that the machine understands. Okay, so the machine level language are hex instruction sets like what we see here. Okay, and right hand side, left hand side. Okay, so what will be on the right hand side? Okay, what will be on the right hand side is high level language such as C programming, Python, you know, whatever that you can think of wiring language, these need to be compiled. Okay, so what is slightly towards nearer to the left hand side, your machine language is assembly language. They're actually quite near. There is no two ways to interpret, you know, machine language. They are actually quite near. They're just one way to interpret, but C can be interpreted very differently when converted into machine language. So remember this illustration, your right hand and your left hand. Okay, right hand, high level programming language. Left hand means very low level machine language. Okay, and these machine language are things that we cannot read, but somewhere along that line from the right to the left is an assembly language which human can read and is very near to machine language. So if I were to ask you, if you put in your resume and you say that, hey, sir, I know I'm applying for a job as an embedded system engineer, and I know wiring language, you know, Arduino, I know C programming. Let me tell you, those are nothing. Okay, you should put stuff like, you know, I know register transfer notation, expression. I know machine language. I can read machine language. Wow, that will be very impressive. But nobody does that. All right. So you can say that, well, I'm very familiar with assembly language. You know, these are the things that actually what the technical people wants. Okay. Your 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 experience in doing C programming is hobbies level. Right. So these are things that are even the high school kids can do. Okay, another thing that you can express your competency is actually through your experience in developing libraries. Okay, can you develop libraries, you know, for your projects, you know, and you know, you give a resounding yes, I can develop libraries in assembly language. Wow, that will be a solid answer. All right. So to avoid using binary and hex, it's very difficult to read. Can you understand what is 480D? It's possible. Some of you might be even possible. I won't go to the extreme to try to understand this, but to avoid understanding things in binary, scientists, engineers develop a slightly higher level, just slightly, okay, using assembly language, so that they're able to understand slightly better. All right. Again, you can program anything in assembly language. Very optimal. One page of assembly language will be equals to one line of C programming. So that's how optimal, how low level the assembly language is. Again, don't be confused by the term low level language. Oh, these are stupid things, you know. Low level language means you are actually very near to communicating with the computer in its native language, the machine language, okay? So you're able to reach that level means you are actually quite capable, okay? And you already have a general knowledge of assembly language from the MIPS architecture from, I actually do not know whether whatever that you guys learn, I assume that you know a bit, huh? You should be able to start coding in assembly language. Later in the semester in the lab, we go about assembly programming. Okay, I hope you reach that level. Programmers write program using text processor generated to generate source file. Okay, so you write it in Notepad or whatever in assembly language. Then you generate a source file. Okay, the source file contains assembly language, directive, instruction, command, and macro. What's a macro? Macro is it's basically an assembly language equivalent to function in C programming. Okay, so I want to write a function. Okay, I want to write a function, and you do so by writing a macro. Okay, so it's equivalent to a function. You can do so. Okay, source file is fed to an assembler that expands the macros and translate assembly language into machine language. So you will have different macros. You will have different macros, and the assembler actually convert all these macro that you included in your program into an object file, generating an object file. And these are the object files that you need to load inside your embedded system. Interpreters are special type of assemblers that interpret assembly language in a program one line at a time. So this is an interpreter. Again, assembly language is quite near, but there is still a bit of variances, and this is the function of the interpreter. All right. The object file is sent to the linker, which combines the file with previously assembled files, libraries, and generate an executable file. So this is the executable file that is loaded into your MCU memory. So whatever that you see, the hexadecimals that you see, that is what you see, actually, the executable file. Okay. Don't confuse with the executable file that you see you always use in your desktop. Okay. This refers to assembly language, compiled assembly language. Okay. So to parse assembly, run more than over the text source probably to identify labels and constants. So this is the process of what your IAR actually do. These are all just reading stuff. You can go through the lecture slides and the book, but these are just the process, several process. Now, should we learn about this? Why is it so complicated? But when you press compile, everything is actually done by your IAR. You know, look at Arduino, it's even easier because the program, the IDE, is designed in such a way that it really makes the work of the user so easy. Okay, that's why a lot of people go for all this kind of Arduino and stuff like that. But the code is never optimized. All right, remember, as an engineer, engineering means optimizing. There's one word of actually expressing what is engineering. Engineering means optimizing. Okay, a lot of things that you do for your FYP or whatever is all about optimizing, achieving. You have something. Okay, you have a robot that works. You know, it already worked. Many people discovered it. You know, the robot arms. This is the algorithm, pick and paste. You know, or whatever. But the job today at our current scenario, what is research? Our research in engineering is mostly on optimizing something. Okay, so you go to the chemical or chemical department, they will also have a lot of optimization. You go to the mechanical department, they will also have a lot of optimization. Generally, engineering means optimization. Okay, so it's always optimizing something. Okay, you cannot say write a research proposal and says that, well, my machine works. It doesn't work that way. Okay, for engineering terms, you have to present an optimized solution. Okay, so that's why assembly language is important. The knowledge, you can always do it in C, whatever language. It's never optimal. Okay, that's good enough for you to explore, but you want to go further to very competent and to be able to say that, to your interviewers, your potential interviewers, I'm very well versed and I'm very competent in assembly language. Well, if you claim that in your CV, you should be able to do so. In your So this is the whole process of from the notepad. You write your text file in your notepad until you get something that you can burn inside your memory. So these are the things that your IAR has actually taken care of for you. Okay, so you include the in your assembly language lab, you will have libraries. Okay, so this linker actually try to extract whatever libraries that you included inside the file, convert it into executable file. Okay. Okay. Now we've basically covered what is machine language, what is assembly language, what is RTN, register transfer notation. Now we want to discuss a bit. Again, it's part 1 and part 2. This week is part 1. How many types of assembly language are there? All right. So we have data transfer type, we have arithmetic logic type, and we have a program control type. Generally, just three types of machine learning, and there are about 30 or so, 30 or 40 assembly language instruction sets. So each one affects the flag differently. All right, so you need to roughly know. I won't ask you to memorize. I don't think it's necessary, but it's good for you to know as much as possible about. If you have time, you feel that your future is in embedded system, please go and read about it, right, in the textbook. Okay. This instruction move data. Okay, now we talk about the first type. Move data from one source to destination. Okay, they copy the source without changing the source except for its behavior is swap. The execution of this instruction involves bus interface logic and registers. Flags are usually not affected by this instruction. Okay, so it says that for data transfer, flags are not affected. What flags are we talking about? Remember, we talked about your first tutorial, first or second tutorial, the zero flag, the carry flag, and all these flags. When you do a data transfer, flags are not affected. All right. So you move, load, swap. You can do a swap. Okay, the destination becomes source becomes destination. Then you remember what is a stack. Stack is a stash of memory that you allocated for a very specific reason. Okay, then you have port in, port out. I try to cut it short. I don't think this is okay, this is not important. Okay, so you just need to know. You can read further on this accumulator and things like that, but generally it's a data transfer means you want to transfer data from one memory to another, register to register. All right. Okay, the execution of this instruction uses ALU, register, and bus interface logic. So, okay, your ALU is also involved. This instruction usually affect the flags in SR. Now, this one is arithmetic logic instruction. Okay, so what are arithmetic logic instruction? Plus, minus, divide, things like that. Okay, so if you see, this one is just involving moving. Okay, but the moving the information from one register to another. So these are data transfer. But when it comes to arithmetic affects the zero flag, the carry flag, and all this because it's a mathematical operation. Okay, and it involves ALU, it involves the register, and it involves the logic interface, the bus interface logic. All right. So generally, apart from arithmetic, you also have logical. Logical is and, or, so on and so forth. This one you should know, okay? And types of arithmetic logic instruction, you have compare. Anything that involves just comparing 1 or 0 or whatever, bit compare or whatever. Now, these are categorized under logic operations, okay? So plus, minus, and all these are considered arithmetic. So you can take the list in the book, okay? Try to understand, have a feel of it. What is arithmetic? What is logic operation? Okay. Compare and test. Okay, they realize an operation, you really subtract. So this is important. It's equivalent to your, when you want to program everything in assembly language, this is equivalent to your if else. All right, your famous if else. So I used to do this. We have 5 sensors that are detecting a line, a black color line for competitions, and you know, if line in line 1 equals to black or whatever, so we do a comparison. Okay, then we check the flags. Okay, if they have certain values, means to say that the sensor either register or yes or no. All right. So this one is compare and test. All right. Rotate and shift. Sometimes, for example, you have 1 0 0 0 0 0 0. You just rotate it to the left. You get 0 0 0 0 0 0 1. Okay, so just try rotate left, rotate right. Okay, it's one of those instruction set. Find it in your book, right? Yeah, bitwise operation. Okay, so it allows us to set, clear, modify specific operation. Okay, so these are a category of operations. We call it bitwise operation. You can compare it with masking, like what we did last week. All right, but these are machine language, assembly language. Okay. Now the third category is the instruction that change the flow of the program. Now, what is the equivalent of C? You have your if else, and you also have while loop, and now those are equivalent instruction sets that change the flow of your program. Okay, so it's equivalent to your if or else program. Okay, conditional jump means to say that if this condition I jump, I skip this instructions. Conditional jump, unconditional jump means I jump, I just jump without having any conditions, without exploring whether the Z flag is on or the carry flag is on, whatever. Conditional jump, you look at the flags, and then you have your subroutine and return. Okay, this one you can explore more in your book. Even if you look at my slide right now, not much information given. But look into the instruction sets, unconditional, conditional, jump. Okay, what do they mean? We will explore this in lecture 2. So even if you're lazy, it's fine. All right, we will explore this. All right. These special subsections, you have subroutine calls and return, equivalent to your interrupt in your C programming. Okay, so you can look at it like this. All right. Okay, now these are examples of a flow affecting program. You have your jump if 0. If the 0 bit is equal to 1, then you jump. Jump if not 0. Jump if carry. Jump if no carry. So these are, they refer to the status register. Okay, if status register is either 1 or 0, this one will actually, now why do we need this? This is equivalent to your, like what I said, in your machine language, in your assembly language, there's no such thing as if else. No, you won't find this code, but it's only in your C. But in the assembly language, you have jump and you have JC, JNC, JNZ. These are equivalent to your if and else. All right. Okay, this is an application of jump. Okay, so looking at, just by looking at the Z flag, you can skip certain parts of the program. So equivalent to your if else loop. Okay, so we will actually explore the each of these instruction more, have some practice. But at the moment, it's good for you to just have a look at whatever that we've learned. Okay, so today a bit of recap. We've actually explored first attempt at exploring assembly language in an in-depth way, rotation, register transfer notation, and the machine language. Okay, so see you guys this week for tutorial. Please check out some of the tutorials, and happy holiday for those Sarawakians, Malaysia Day. Okay, not only for Sarawakians, whole Malaysia. Happy Malaysia Day. All right, so that's all for this week. See you guys again.